Let's say that we have two lines in space. Now, since I'm using Sharpies to represent the two lines, we know that they don't intersect because the Sharpies can't pass through one another. If I move these around and keep them more or less in the same relative orientation, we can see that the red Sharpie passes over the blue Sharpie. Now, it's difficult to represent that situation with two lines drawn on a flat piece of paper, but I'm going to make this line somewhat red-blue and indicate that maybe this line here represents this Sharpie, this line represents this Sharpie, and I just want to point out that the perpendicular to these two lines, I might have to set one of these down, a line perpendicular to both of these, it looks something like this. Okay? Now, I'm trying to represent that in the plane, and I'm going to let P and Q be two lines on a perpendicular between these two lines. And I'll say that if a line, let me put these in slightly different orientation. Let's use the blue one down here. The point where we're perpendicular to both of these lines is going to be the point at which the lines make their closest approach. We can prove that, but right now we're just going to assert it. So my picture here represents a point P on one line that we'll call maybe the blue line, and a point Q on another line, which we'll call maybe the red line. And let's go ahead and put a blue circle around P and a red circle around Q. Along the mutual perpendicular of closest approach. This means that this angle here has to be a right angle, and this angle here has to be a right angle. And of course, these planes these lines are a flat representation of something in 3 dimensions, so you have to use a little bit of imagination. In any case, these are the points of closest approach, and those occur when PQ is perpendicular to both lines. Now, the question we want to think about is, how close do these lines get? So, we'll write that down here. How close do the lines get? Or, what is the distance between the lines? And we could say, what's the distance of closest approach? How close are they when the segment from here to here is perpendicular? Okay, well, let's say that we bring this out and rotate it so that everything is a little bit more in a plane. And we have our point P here, our point Q here. And P0 and Q0 represent any points at all on these two lines, with the only restriction being P0 lies on one line, Q0 lies on another line. So this vector here is the vector P0, Q0. I didn't leave myself a lot of room, but I'm going to draw a little arrow over the top of that label. And we can represent the situation now, especially if we put a head on the vector PQ. We can isolate these two vectors, give them a common initial point, and we can illustrate the situation. Okay, P0, Q0 is a vector between 2 points of the line, of the two lines, 1 point on each line. PQ is the vector that's perpendicular to both lines and has a magnitude equal to the distance. In any case, if we project the vector P0, Q0 onto the vector PQ, then we should get the distance of the vector PQ. Now, I've mindlessly sketched a projection line that comes down here and doesn't come to the end of PQ, and really this picture should look like this. Here's P naught, Q naught. Here's PQ. And if we're in the plane defined by these two vectors, PQ is the projection of P naught, Q naught onto itself. In any case, we're going to maybe kind of blot out that projection and emphasize this projection. Now, the lines, let's just say we have two different forms of the equations of these lines. The lines are, let's say, in parametric form. The first line is x minus 2 over 4 equals y minus 3 over 7 equals negative z plus 1 over 5. The second line is perhaps indicated by xyz plus 413, xyz equals 413 plus t times this vector. And we want to take these two different equations of the lines, reconcile them, and determine what is the distance between the two lines. What's the distance along a line that's mutually perpendicular to both?